Okay, so let's get started. So first, just some quick reminder on the logistics. So please mute yourself during the talk, but you are encouraged to turn on your video so we can see some live faces. And if you have quick clarification questions, please post those in the chat box. I'm going to monitor the chat box and relay those questions to the speaker. And if you have longer questions, there's going to be some question breaks in the middle and also a Q&A session at the end. Okay. So today it's our pleasure to have Ramesh Johari as our speaker. Ramesh is a professor at Stanford University with the full-time appointment in the Department of Management Science and Engineering and the courtesy appointments in computer science and electrical engineering. So he is a member of the Operations Research Group and the Social Algorithms Lab in MSNE, the Information Systems Lab in EE, and the Institute for Computational and Mathematical Engineering. He is also an associate director of Stanford Data Science. He received an AB in mathematics from Harvard, a certificate of advanced study in mathematics from Cambridge, and a PhD in electrical engineering and computer science from MIT. He served as co-chair of the ACM-EC program committee in 2019, and he is an area co-editor of the revenue management and the market analytics area for operations research, and the associate editor for management science and stochastic systems. So his research interests are in online platform and marketplace design, experimentation, and data science for online platforms. And more recently, application of these techniques to personalize the healthcare via telemedicine. So we have to know what telemedicine is. So, okay, so today he's going to talk about interference in experimental design in online platforms. Let's welcome Ramesh. Ramesh, the floor is yours.
Great, thank you. Wena, you can still hear me okay? Everything's good on audio? Great, yeah. Well, thanks a lot for inviting me. This is a really impressive seminar series that's been put together. And of course, these events are great during the pandemic. Really nice to see so many familiar names. I know there's a few of you that may have seen a version of this talk over the summer. And so I apologize for those of you for whom it's slightly redundant, but you know, I think in this talk, at least one of the things I'll try to do is emphasize the role that applied probabilists can play in thinking about some of these questions. In the abstract, I said that I'm going to try to talk about two different pieces of work. In preparing the talk, I'm going to focus the bulk of the talk on this work with Hannah Lee, Inessa Liskovich, and Gabriel Weintraub. And I'll have a few slides at the end that are a little bit more expansive and forward-looking. And we'll return to some of the other stuff I mentioned in the abstract then. Okay, so with that in mind, let's see. Let me first, talk about just the overall motivation. I'm guessing that many people here have heard the phrase A/B testing and in some fashion in the past. A/B testing just refers to the fact that online platforms typically use randomized controlled trials to test basically anything. This can range from changes in a web page, so like changing from a red web page to a green web page, over to new features, features by which participants interact with each other, for example. And typically the goal is for the platform to estimate the difference between the performance that they see when the entire platform is under the control universe and the performance they would see if the entire platform is in the treatment universe. Okay, so this is kind of a standard use case of experimentation. And kind of the overarching theme of the talk is that in marketplaces and online platforms, you can have what's called interference due to competition between participants in the market. And this competition can lead to biased estimates of the actual difference between global treatment and global control. Roughly speaking, at a high level, the source of this kind of interference is that demand competes for the same set of supply and supply competes for the same set of demand. So I think rather than talking about it in the abstract, and especially in an audience where we're all kind of coming from different backgrounds and problems that we focus on, let's just take a super simple example and walk through it so we understand the phenomenon I'm talking about. So, in this example, just as a caricature, imagine an online labor platform where you have freelancers and you have customers that can hire these freelancers. Okay. So a typical form of experimentation, let's suppose there's a new feature that the platform is planning on rolling out that makes customers more likely to hire freelancers. So one way that the platform might decide to test this feature is to give the feature to some customers and not to others. And that would be what's called a customer side experiment. Okay. So in this customer side experiment, in particular, suppose that customer A is assigned to the treatment group and customer B is assigned to the control group. And customer A is more likely to book the freelancer. So suppose customer A arrives and books this freelancer, takes them off the market. Then what happens is that now when customer B arrives, there is no one left to book. So it's true that customer B is less likely to book than customer A. But when we observe that customer B didn't book, this isn't so much because of the fact that customer B has a lower booking likelihood. It's just because customer B had no inventory to book in the first place. So that effect, that customer B's outcome, whether or not they book somebody, depends on the treatment assignment of customer A. That's referred to as interference in experimental design. And this is happening because both customers A and B are interacting with the same set of supply on the other side of the market, in this case, the freelancers. So there's nothing left for customer B to book. So this competition between customers leads us to underestimate the bookings in global control, because on average, customers in the control group see less available supply than they would see if the entire universe was global control. And conversely, it leads us to overestimate the extent to which bookings would be made by the treatment group, because essentially what they're doing is they're stealing freelancers away from the control group. So the way you want to think about this is, how would the world have looked different if everybody was in treatment or everybody was in control? So the idea is that in the experiment, control customers on average see lower available supply than they would see if everybody was in control. Treatment customers on average see greater available supply than they would see if everybody was in treatment. So that leads us to incorrectly estimate the benefits of the treatment over control if it was rolled out to the entire marketplace. So let me pause for a second here, and I'll just ask if there's any questions. So what's the difference between clinical trials and this? Actually, that's a great question. There's not really any difference between clinical trials and this, at least from the perspective of what platforms are doing. A/B testing is really just a fancy name for randomized controlled trials. So in that sense, it's the same. It's also the case in clinical trial design that you often have to think about types of interference that can arise between the treatment and control groups, especially when, for example, the clinical trial design involves something like encouragement rather than direct intervention through the treatment. In our case, the main difference in this talk is that we're focused specifically on experiments that are run in these two-sided online platforms. And kind of a key feature of experiments in these platforms is that because we have constrained demand and constrained supply, the competition between demand and the competition between supply actually lead to interference that we can structure and analyze. So it's kind of a novel type of interference that arises in a context in which we can give it some mathematical structure and actually say something about it analytically. So I'd say that's the main focus of the talk. And in fact, that's actually kind of good motivation for the next two slides. That you might ask, like, how big can this bias be? There's empirical work that suggests this bias can actually be as large as the treatment effect. So if it's that large, then you may not even be correctly understanding the potential value of the intervention. And I think from our perspective, the main motivation for this work was that there's not really a lot of consensus on conditions under which the bias might be large, or what kinds of experimental designs and associated estimators actually do a good job of minimizing that bias, as well as variance. In this talk, I'm going to focus primarily on the bias, but there's associated interesting questions related to variance as well. So let me quickly describe the contributions here. So as far as this paper with Hannah, Inessa, and Gabriel is concerned, the main contributions are that we develop a formal framework to study the performance of experiment designs and estimators in two-sided platforms. I will say that for this audience, something that I really like about this paper just from a, I'd say from a technical perspective, is that I really like the underlying model that we were able to work with to derive these results. Essentially, what it amounts to is a closed queuing network with a particularly unusual type of dynamic to it. And so I'll describe that in more detail, but I think this is something to take away, is that there is a substrate in this paper that I think is a setting in which many additional analyses beyond just the ones we did here could be carried out. So our goal is first to propose that model and to provide some structure through that model. But then on top of that, we're actually able to derive quite a bit of insight. We find that biases of common designs and estimators depend on the supply and demand imbalance. And I'll explain sort of exactly how this works out, but roughly speaking, the high level takeaway here is going to be that if there's more supply than demand, then the design that randomizes on the demand side actually yields lower bias. If there's less supply than demand, then the design that randomizes on the supply side yields lower bias. And I'll try to explain that comment, that kind of high level point as we go along. In addition, there's another piece of our work where we actually try to introduce a new design that actually randomizes on both sides of the market simultaneously, and propose some associated estimators that perform better than designs that only randomize on one side of the market. So I'll talk more about that as well. And I think, again, just going back to the high level point about the model, I think this is really the tip of the iceberg in starting to understand different experimental designs and estimators that could be used. And so I do think that even within the context of our model, there's a lot of room to play and a lot of interesting potential design challenges there. And at the end of the talk, what I'll do is I'll kind of zoom out a little bit, talk about ongoing and related work broadly in my research in this space, including alternative experimental approaches and some open directions of interest. Okay, so let me just pause again one more time, ask if anyone has any questions on the motivation or anything.
So there's a question in the chat box. The question is, what's the difference between clinical trials and this? And
yeah, so yeah, that was the one that I was answering earlier, just about the fact that A/B testing is the same as randomized clinical trials, randomized controlled trials, sorry, and so in that sense, it's just a modern name for an old thing. But the main thing I want to emphasize in the talk is that idea of interference through a marketplace. I should add, by the way, for those of you that are familiar with the space, maybe through kind of broader exposure to the area, there's been a large amount of work in the last, I'd say, decade or so, maybe even a bit longer, that's really focused on network interference, where you have experimentation and the experimental units are nodes of a network, and the edges in the network govern interference relationships between the experimental units. So, if I'm a treatment node and I'm surrounded by control nodes, then the fact that my neighbors are control will influence my potential outcome. And so, our work actually bears a lot of relationship to that line of work. It kind of falls in that space. The main distinction is that we're working with a much more structured model of those interactions, where we actually explicitly describe the marketplace. So with that, let me actually go into the description of the market model. So what we do is we consider a two-sided market model in which there is some asymmetry here. One side is supply and the other side is demand. And I'm going to use terminology that says that customers book listings. So listings are supply, customers are demand. From the perspective of describing what's going on here, the important thing that I want you to understand is that the number of listings, the total number of listings in the market, remains fixed over time at capital N. And what happens as the customers arrive is they can book listings. The listings will become occupied for some amount of time and then become available again. So the goal is to kind of describe that entire stochastic model. Okay, so the total number of listings is fixed at N, all right? Each listing can have a type, theta, and we don't actually do any estimation assuming that we have knowledge of types. So throughout the entire talk, anytime I mention types, those are always, those could be latent. They may be something that the platform does not observe, okay? We're going to focus on estimators that are type agnostic. But the idea behind types is that at least this allows us to have heterogeneity in the listings and then how they behave dynamically. We do assume this is a finite set. I think certainly an interesting question would be to consider, generalization of the kinds of results we have here to a setting where theta need not be finite. This n is sort of suggestively named to be a scaling parameter. The analysis that we will do of bias is in a regime where we scale n to infinity, in a mean field limit where we scale n to infinity. So I'll talk about that as well. Okay, so we assume that the fraction of listings of type theta converges to rho of theta as n goes to infinity. So rho is a distribution over the type set, and the fraction of listings of type theta converges as n goes to infinity. So that'll be relevant when we take this scaling limit with large n. Okay, so now again, describing sort of the dynamics of the marketplace, how does that proceed? At each time, a listing can be available or booked. So think of these, as so a listing in this case, let's say like individual freelancers in an online labor market, we think of as a listing. And each of these colors corresponds to a different type of freelancer. And the kind of shading out here of the freelancer represents the fact that they're booked. So in this case, we have 6 listings, 3 of which are available. All right. And then the other 3 are booked. What we do is we represent the state of the system as the number of available listings of each type at time t. So in this case, for example, we have the state being 1 yellow freelancer is available, 1 blue freelancer available, 1 green freelancer is available. And the composite state vector is bold sigma t. Now it's a, again, like I'm forecasting a little bit here. By calling this the state, I'm implicitly telling you that all the dynamics of the system are only going to depend on this state. And I need to fill that picture in a little bit to show you exactly why it is that with respect to this state, we get a well-defined process that we can analyze. But for now, take my word that that's where we're headed. And this will be the state representation of the market. Notably, again, just to remind you, I'm not assuming necessarily that the platform observes theta and therefore that the platform observes this state. The platform can certainly observe how many freelancers are available in aggregate, how many listings are available, but they may not know how many of each type are available. And so the estimators we define will not depend on type knowledge. Again, just to emphasize that point. Okay, so then what do the customers do? And the idea, so I'm going to describe this in 2 steps, one at a high level and then one with a little bit more detail. So upon arrival, a customer is going to choose a pool of listings that we call their consideration set. And the way to think about this is imagine that you're going to a site like Airbnb. When you go to Airbnb and you run a search, it pulls up a collection of listings that you look at from which you will eventually decide if you're going to make a choice. So this consideration set is a sampling procedure that kind of determines that universe from which the customer may potentially make a choice. Okay. And then they choose which item, if any, from the consideration set to book or to rent. So we need to describe these 2 pieces of the process to explain how the customer from arrival eventually gets to a booking. When I say customers arrive over time, I want to make clear that what's happening here is that customers are arriving according to a Poisson process. They arrive once, they sample a consideration set, choose whether to book something or not out of the consideration set, and then they leave forever. So our model is asymmetric in the sense that listings are long-lived and customers are short-lived. Okay. So customers only arrive and act once and then leave. The type of a customer is represented by gamma. And again, as before, the customer type may be latent. Customers of type gamma arrive at rate lambda gamma. And in general, throughout the talk, the customer types will be subscripts and the listing types will be arguments to functions. Okay, so just as a way to distinguish between the 2. So there's an important primitive in the model that this process gives rise to, which is what we call the choice probability. And the choice probability is the probability that an arriving customer of type gamma rents a listing or books a listing of type theta when the system state is sigma. Okay, so this kind of choice probability is the result of a more precise formal description of the process by which consideration and choice happen. So for any given system state, I need to describe to you how the system state induces consideration sets, then how customers make choices from the consideration set. So Maria asks, is the state of the system observable to the customer? Not directly, but also I'm going to mechanically describe for you the choice model in the next slide here. And you'll see that in some sense, the state of the system is clearly influencing what the customer will be able to see as being available. So let's just work out how that happens. So when a customer arrives, now I've actually made all of these solid colored. None of them are faded, so all of these are available. So this is the spectrum of available listings in the market. And the first step in this choice modeling is that the customer includes each available listing in the consideration set with some probability that depends on the customer's type and the listing type independently across the listings. So informally, what's happening here, first of all, is that different types of customers can have greater or less affinity for different types of listings. So this allows us to capture, in part at least, heterogeneity through search and recommendations. So there may be there may be personalization where some customers care more about certain types of listings than others. The second thing to note is that because of this independence across listings, if the number of listings of a given type is larger, then that also means that that there's a greater chance that those listings will show up in the consideration set of the customer. So back to Maria's point, the customer is really making a choice out of that consideration set. So they're not necessarily directly interacting with the entire system state. But it is the case that if more listings of a given type are available in the system, then there will be a greater probability of those arising in the customer's consideration set. Okay, so after this consideration set is formed, right? So this is the step where the consideration set is created. In this case, one yellow, one blue, and one green listing appear in the consideration set. The next step is that the customer makes a choice from the items in the consideration set according to a multinomial logit model with some outside option. Now, what does multinomial logit with some outside option mean? Essentially, it means that the customer has a utility for each of these items that can depend on their own type. So again, we have type-specific utility that's indexed by the type of the customer and the type of the listing. And the probability that a customer chooses a given listing in this set is that that utility for that type divided by the sum of the outside option and the utilities of all the available listings in that consideration set. So in particular, what this means is that the probability of choosing the outside option is E gamma divided by the same denominator. This is a very standard discrete choice model. Obviously, huge amounts of structure to the multinomial logit choice model. That would probably be an entire talk in and of itself. For our purposes, this is a really convenient way of capturing the fact that customers have a probabilistic choice that's happening through this consideration set. I want to just pause here for a second and note, that well, actually, let's see. Let me just finish the few animations on the slide. So, the customer may choose not to book. They may choose to book one of these things. So in this case, let's say they book the green listing. Then when you return to the system state, the way that influences the system state is that now the system state has the same set of listings as before, but one of them is marked unavailable. And this kind of explains why the correct representation of system state for our model is exactly that vector of available listings of each type. So just stepping back for a second, one thing I want to mention to everyone here is that of all the things in this work, the thing I think that is richest for potential investigation and thinking about potential extensions and differences is exactly this process of consideration and choice. Maybe before that, let me answer a couple of the questions in the chat. So Ramesh asks, so the customer may leave the system without choosing any option. Absolutely, yes. That's really important. As a very basic thing, probably one of the most important things that a platform will be interested in is just whether an intervention increases the booking rate at all. And so in order to talk about the possibility that an intervention can increase the booking rate, you have to start by presuming that there's some rate at which people don't book anything when they arrive, and then ask whether that rate of not booking decreases, so the rate of booking increases. Anastasios asks, how is the consideration set formed? Is it customer dependent, i.e. on internal customer features? Yes, so remember the consideration set formation process is this independent sampling with these probabilities. So theta L here is the type of listing L in the current state of the system. And alpha gamma of theta L is a probability that a customer of type gamma selects a listing of type theta to include in their consideration set. So these alpha, gamma, theta are primitive parameters of the model that allow customer type and listing type specific probabilities of selection into the consideration set. Now, beyond that, you could imagine something where there's also idiosyncratic variation at the customer level, so that when customers arrive, you have additional heterogeneity that's not only captured by the types, and that's not part of the model that we have here. But that would be one of the directions where you could try to extend things, potentially by having a richer type space, something where there's continuous covariates for both listings and customers. I think the other thing I would mention here is that, some of the other interesting types of directions to take this that would be different from the way we did it is you might imagine that instead of having something where you're sampling, effectively what this does is the representation of listings of different types in the consideration set will be proportional to the masses of those listings that were available in the market at large when the customer arrived. And I think something that you could imagine would be different from that is something where customers are really making a binary choice of whether to include even one listing of a given type in their consideration set first. So that's a much more nonlinear model with respect to the underlying volume of a given type that's available. So maybe said differently, if you go to Amazon and you're looking at a consideration set, the question here is if there's 1,000 books of a given type in Amazon's inventory, and 1,000 copies of a given book and 10 copies of another book, then do you sample 100 times more of the book that has 1,000 copies? And that's probably not true. You probably only are, looking for one, considering at most one copy of each. So Amber asks, can two options of the same type be included in the consideration set? Yeah, and that's actually exactly the question I was just addressing, Amber. That's exactly right. That, yeah, because of this consideration model, because it's independent probabilistic choice over each copy, in fact, yeah, you could be sampling so that two copies enter the consideration set. Christina asks, the alpha parameter just reflects the customer's choice, or is it a parameter that the platform sets in terms of curating the available list shown to the customer? That's a great question, actually. I think it can be, in our model, we introduced this alpha because it allows us to capture a wide range of reasons why you would have customer to listing specific heterogeneity in consideration. One of those is certainly that it could be platform driven. And, so if it's platform driven, then alpha itself may be something that changes when you move from control to treatment, as I'll mention later. On the other hand, it could be something which is simply about idiosyncratic customer preferences. And so at some level, like both of the two things that you mentioned could be captured through that same modeling choice here. Okay. All right, great. Well, thanks for all the questions. That helps me make sure that people are understanding what's happening. Maybe one thing that I'll mention here is that if you think about what's going on in this process, notice that the customer is making a choice among the listings in their consideration set. And so effectively what's going on is that from listings perspective, there's competition between them to be selected by the customer. One of the things I want to emphasize throughout the talk is that when you see the word competition, in other words, there's competition between listings, there's competition between customers, that maps onto interference in a statistical sense. And that's actually one of the things I find most interesting about this work is a connection between the economic concept of competition and the statistical concept of interference. And you'll see this recur throughout. So this competition between listings will be directly responsible for a particular type of interference that will occur when we consider experiments. Okay. All right, so let me quickly walk through the rest of the dynamics so that I can state the mean field result. Now the rest of it's kind of straightforward. So this is the new available listing vector. If a customer books that type theta listing, this closed queuing network aspect of it is that listing then remains booked for an exponential time with some parameter that can be listing type specific, tau of theta. And in particular, what this means is that when subsequent customers arrive, that listing, if it had been booked, this shaded green listing may remain booked even when a subsequent customer arrives. Okay, and so the fact that subsequent customers see an available state vector that is influenced by what happened through customers before them, that is competition between customers, and that'll be the other main source of interference as we go through the analysis. Okay. So for this audience, the next 4 slides, I think, are the part that will be sort of the most familiar. The way I've defined it now, with Poisson arrivals, exponential holding times for the listings, the state becomes a continuous time Markov chain. It is difficult to analyze directly because of this complex choice behavior. And in particular, when I say difficult to analyze, what I mean is that our goal was really to get sort of crisp insight into the behavior of bias. And in order to do that, what we do is we consider a mean field limit where the outside option scales to epsilon gamma. So we're actually scaling the value of the outside option with n. And the arrival rate also scales up. And in particular, n itself goes to infinity. So the number of listings in the market is going to infinity. For later reference, I'm going to refer to lambda as the sum of these limiting arrival rates. So just remember that notation. I'll come back to it later. Okay, so in this limiting regime with n going to infinity, arrival rates going to infinity, and the outside option value going to infinity, what we can show is this mean field limit result that the scaled version of the state converges. I put that in quotes. I'll tell you in 2 slides exactly the formal notion of convergence that comes from Kurtz's theorem. It converges to the solution of a limit ODE that's given here. And this limit ODE actually has a very natural interpretation where this first term is the replenishment rate in the market. So remember, rho of theta is the total mass, the fraction of listings of type theta in the limiting market. This is the mass of available listings in the limiting market. So this minus that is the mass of occupied listings in the limiting market of type theta. And that's the rate at which they become available. So this is the replenishment rate of listings of type theta. And then this is the rate. Lambda gamma is the arrival rate of customers of type gamma. This P gamma is a limiting choice probability of listings of type theta, given the current state vector of the market. And so that's the rate at which listings of type theta are booked. So replenishment minus booking accounts for the change in time of the available listings of type theta. Okay, and so this ODE has a unique limit as t goes to infinity, and that's what we call the mean field steady state. All the analysis in the remainder of the talk is of this mean field steady state. So there's basically 2 pieces to this result. One is stochastic convergence to this hydrodynamic limit, to this fluid limit. And the other is establishing that steady state actually has a unique limit. And we do it in reverse. We first establish the ODE has that unique limit so that we can apply Kurtz's theorem to obtain the fluid limit. So I'll quickly mention these 2 pieces of it. So to establish that the ODE has a unique limit, this is one of those things that, I mean, I guess for anyone who's done this kind of work, I always find it extremely remarkable when there's the Lyapunov function lurking in the background. It always feels somewhat magical. So again, the same is true here. There is, in fact, a Lyapunov function for those ODE dynamics that, roughly speaking, takes the form of it's sort of a related to a log sum x type of Lyapunov argument. Here, what's happening is that this you can see the shape here, the contours here of the integral of that ODE. The interesting thing is that this Lyapunov function is not actually convex on its own. But if we apply the transformation where we define y of theta to be log s of theta, then this actually becomes a strictly convex objective. And we can use that to establish uniqueness of the limit point. And the structure of this Lyapunov function then actually helps us analyze the ODE as well. Okay, so that's part 1 of the argument, to get a unique solution to the ODE using a Lyapunov function. And then finally, we can apply Kurtz's theorem to establish this convergence to the limit ODE in this form. And kind of the key idea here is really to establish that choice probability, remember, this is in the finite system. This really should have a superscript n on here. In the finite system, we have the probability that a customer who sees the system in state sigma, the probability they choose a listing of type theta, that converges to a well-defined functional form that looks like a logit choice model. You notice this logit choice model now has an alpha in front and an S here. So the alpha here represents the fact that customers are sampling listings of type theta according to this probability. This is the utility of a listing of type theta, and this is the total mass of listings of type theta that are available in that fluid limit. So what this choice model is saying is that the probability I choose I book a listing of type theta, the probability I book a listing of type theta increases as the mass of available listings of type theta increases as the utility of this customer type for that listing increases as the sampling probability of this customer type for that listing type increases. So Marnoush asked, what was y of theta in the previous slide to make it convex? Let me just go back there. So we define y of theta to be log s of theta. So this expression is defined in terms of s of theta, transform variables to y of theta. Now view this as an optimization problem over the vector y. And this optimization problem is strictly convex in the vector y. That was the kind of key transformation step that we needed to be able to establish strict convexity. Now, yeah, and just to be just a minor technical thing here, obviously, if I take log s of theta, the domain of this becomes minus infinity to log rho. Okay. Okay, so that's the kind of mean field limit argument. And maybe before I move on, let me pause here and just ask if there's any questions on sort of that's the end of the model development, the technical development of how the model works. And I'm going to now walk through the slides that describe kind of our main insights with this model in an experimental setting. And the remainder of the talk does not have the same level of technical detail as what I presented here. I'm going to present it a little more informally, relatively speaking. But I want to make sure that everybody's on the same page with what the model looks like. And again, if you were to drop off the talk now, I think the thing to take away from this is that I'm going to give you some things that we learned by working with this model. But I also think this approach to thinking about experimental design in platforms with inventory dynamics is actually a really good way to contribute to this literature on experimental design and estimation. There's a large number of questions where bringing the toolkit that we have in analysis of queuing models like this actually can be quite valuable in understanding the types of interference that arise due to constrained inventory. So I think that's kind of the high level point, is that for this audience at least, this was a really nice way to build a stochastic model on which we actually can contribute meaningfully to understanding experimental design in these settings. Okay. I know that sounds like a concluding statement, but I'm actually just about to start the rest of my main results. Let me see if anyone has any other questions before I go on. Okay, all right, so with that, let me keep going. So good, so I'm going to step through this, again, like I said, I'm not going to present it at the same level of formalism as before. In the paper, what we do is we consider interventions that change the parameters that influence the choice probability. So these might be, for example, that alpha gamma or the utility or the outside option. Without loss of generality, we actually focus on listings that just change V. And that's without loss of generality because you can reparameterize a change in one of the other two into a change in V. So this is just because of the structure of the choice model. So what I want you to imagine is that there's some intervention that changes V into some different V. In fact, to keep things simple for the rest of what I'm about to say, you'll actually understand almost everything as long as you just assume there's only a single customer type and a single listing type. So in that case, there's just a single utility V that a customer has for an available listing. Imagine that treatment raises that utility from V to some V tilde. And that's the intervention. So the intervention is essentially something that makes listings more attractive to customers. Okay, so for the remainder of what I'm going to say, don't worry about heterogeneity of customers. Don't worry about heterogeneity of listings. Just think of treatment as something that takes the value that a listing has to a customer and raises it. And so the platform wants to know, if I raise the value of the listing with my intervention, how much more will customers book listings? Okay, so that's kind of what we're going to focus on. How does the steady state booking rate change relative to control? All right. Okay, there's three worlds of interest to us that we're going to use our model to study. So this is, again, what I really like about this underlying stochastic model is we can use it to describe each of these three worlds. In global control, every customer sees every listing as control. So imagine just writing down that entire model, but where every customer's utility for listings is V. And you just go through the analysis and get to a mean field steady state of the resulting model. Same thing with treatment. Imagine that every customer's utility for every listing is that V tilde higher than V, some utility higher than V. And then there's the experiment. That's the third world, the one where some customers see listings with a higher utility, the treatment customers. Some customers see listings with a lower utility. So how do we model that? The formal mapping to the model is essentially that for every original customer or listing type, we create two types, a control type and a treatment type. And then we define the dynamics accordingly. If either the customer or the listing are of control type, then the utility remains V. And if both the customer and the listing are of treatment type, then the utility becomes V tilde. Okay, and this I know I'm not defining as formally. That's sort of deliberate, due to sort of time considerations. What I'm going to do is I'm going to step you through two examples that'll hopefully make really clear how this translates into our model. Okay. Before I do that, I need to tell you what we're actually trying to estimate. And just a reminder here, what we care about is what we call the global treatment effect at the beginning, is the difference in performance between a world in which everything is the treatment universe, all customers have high utility for listings, and the control universe, the baseline setting that we started with. So what we want to do is we want to compare the steady state rate of bookings and global treatment to the steady state rate of bookings and global control. Okay. And I guess I just want to emphasize this point. I'm going to keep talking about things as if there's only one type of customer and one type of listing. Everything we do in the paper is for the general model, where you have heterogeneity, arbitrary finite type space of customers and listings. But I'll just talk about things through a bit more simple setting. So as I said, I want to consider two simple examples just to illustrate for you kind of how the model fits together with what we're doing here, where, and these simple examples are actually the most common way that platforms will run A/B tests to estimate this difference in booking rates, okay? And these are what are called customer side and listing side experiments, similar to the very simple example we talked about at the very beginning of the talk. So in customer side randomization, okay, what happens is I'm going to, again, assume that listings and customers are completely homogeneous pre-treatment. So you have an arriving customer, and this customer can be either treatment type or control type after randomization. So the randomization happens in assigning the customer to one of the treatment or control groups. If they're treatment type, then their post-treatment utility for a listing is V tilde, which we're going to assume is greater than V for purposes of illustration in our kind of simple example. So the customer's view of the market, if they get assigned to treatment, is that all listings have this higher utility. Their view of the market, if they get assigned to control, is that all listings have this lower utility. And now recall that there's competition between different types of customers, right? Because if I book a listing, that listing becomes unavailable to someone in the future. Notice that although this is the customer's view of the market, if they're treatment or control, it's the same set of 5 listings either way. So if a treatment customer books a listing when they arrive, that same listing will now be unavailable for a control customer if they were to come next. So that competition between customers over time is exactly statistical interference, because a control customer now is being influenced by what a treatment customer before them did. Okay, so this is, again, just back to that point that economic competition leads to statistical interference. And I think that interplay, I'll just stress one more time, is really interesting to me. Okay, so when platforms run this very simple type of experiment, it's also the case that the associated estimator is very simple. What they do is they look at the steady state rate of bookings by customers of treatment type and the steady state rate of bookings by customers of control type. They normalize that by the volumes of customers that are in each of the two groups. And that's their estimated value of the global treatment effect. The CR here refers to customer side randomization. Okay, so this is one version of one type of experiment you could run. Customers arrive, randomized to treatment or control, allow them to book, and now just compare the naive estimate of the booking rate by control customers and the booking rate by treatment customers. All right, and the interference happens because the customers are interacting with the same set of listings. So this basically is the version of the example from the very beginning of the talk. So what was really interesting is that, what we find is that the bias of this type of design depends on the market balance. So here, what I've plotted along the x-axis is the relative demand, which is the rate of customer arrival divided by the rate at which listings become available, tau, when they release. And what we find is that we can prove theoretically that the CR estimator, this naive estimator I defined, is unbiased in the limit where the relative demand becomes very low, in the demand constrained limit, when lambda is very small relative to tau. Okay, so it's probably easiest to get intuition for this by thinking about a regime where tau becomes larger and larger and larger. So remember, tau is the holding time of a listing once it gets booked. So think about a setting where I drive tau up to infinity. So that means, lambda over tau is going to 0. In that world, what's happening is that when a customer arrives, okay, they might book a listing. But if tau is extremely high relative to lambda, then by the time the next customer arrives, that listing that had been booked prior will already be available again. So that newly arriving customer will not feel any interference from anyone that came before them. In other words, every customer who arrives will see the system as if all listings are available if tau is very large, as tau approaches infinity. So, in that world, what's happening is that the customers completely decouple. And so in that case, listings are regenerating quickly enough that there isn't any competition between customers. So this is a really interesting observation. I think this is already interesting to us that in markets that are heavily demand constrained, running that experiment where you randomize only on the demand side is actually quite a reasonable thing to do. And the naive estimate from that is quite reasonable. So this is kind of the first thing that we came up with. And as I said, it's sort of intuitive. If you drive the regeneration rate of listings high enough, then successively arriving customers don't really have an opportunity to interfere with each other. Okay. So let's look at the other side. Let's look at the case where there's listing side randomization. So with listing side randomization, what happens is that we randomize listings into treatment or control. And now when a customer arrives, they will see some listings as being randomized to treatment, some listings as being randomized to control. So the arriving customer's view of the market is going to be this mixture view where some listings are in treatment, some listings are in control. Okay. And we use AL to denote that randomization fraction. So now the interference is that competition between listings I described, because if I am a treatment listing and I'm facing competition from control listings in the customer's consideration set, then I will be more likely to be booked than I would have been if those had also been treatment listings. Okay. So now again, it's the case that the treatment assignment of listings is altering the booking probability of a given listing. So that again, the competition between listings is creating statistical interference in this setting. And so again, the naive estimator here would be to just ask, what's the rate at which treatment listings are booked relative to the rate at which control listings are booked, again, normalized by the relative masses of those two groups. Okay, great. And so for us, this was a really interesting finding out of the paper. There's a real symmetry here that in the same way that customer side randomization performs best when you're demand constrained, it turns out that the listing side randomization naive estimator is unbiased in the supply constraint limit. So here, the orange bars, the bias as a fraction of the global treatment effect goes down as the relative demand increases, as lambda becomes large relative to tau, as the arrival rate of customers becomes large relative to the regeneration rate of listings. So here, the effect is a bit more subtle here. And to understand what's going on, you have to think of it in the following way. So when, if you think about the interference in these experiments, it's because of competition effects between treatment and control listings. But what's happening is that when the supply becomes low, then the main competition becomes between the available listing and the outside option. Relatively speaking, when there's less supply, it also means I face reduced competition from other listings. And actually quantifying that effect is the thing that establishes that you get this unbiasedness in the limit as lambda over tau goes to infinity. So those are, I think, like some of the most important findings out of the paper, that we get this, these really nice behaviors at the extreme. Maybe one thing I'll mention quickly, just to leave enough time for the end, is that we designed this. We offer this new type of design where we randomize customers into treatment with probability AC and listings into treatment with probability AL, and then the intervention only applies when both customers and listings are in treatment. So it's only seen if a treatment customer interacts with the treatment listing. Otherwise, the utilities are always the lower value V. This is also related to independent work by Hito Imbens and Patrick Bayari and co-authors at Amazon. This generalizes both CR and LR by basically, setting the randomization fractions to 1 for either customers or listings. And kind of what's interesting is that if we take this naive estimator that now looks at the rate of booking of treatment customers for treatment listings and compares that to the rate of booking of in these other 3 cells, then we can interpolate between CR and LR based on the market balance. So by setting the amount of customers that are placed into this treatment cell correctly, we can actually interpolate between the two designs. By setting AC and AL correctly, we can interpolate between the two designs. So in particular, defining these to interpolate as a function of market balance can get us between CR and LR. And if we do that, then we can get this green two-sided randomization design that's unbiased in both limits, in the limit of low relative demand and high relative demand. So this is actually something that we're actively pursuing to implement, where we actually use two-sided randomization as a function of market balance to allow us to gain the benefits of both CR and LR in their respective regimes where they're less biased. Okay. All right. I'm going to actually pause on this slide for a second and take a couple of questions before I wrap up. I'm going to try to save maybe like the last 5 minutes to run through my last few slides. We also designed an improved TSR estimator that uses the TSR design to estimate interference between these groups. So actually we add an additional correction for that interference effect. And there's extensive investigation via simulation of the variance behavior of these types of TSR estimators. Okay, so let me see. Do I know how sensitive the numerical values are to my assumption of exponential holding times? Oh, that's a great question. Thank you, Tan. This is like a perfect question from this audience. Honestly, I don't know the answer to that question off the top of my head. I wouldn't read necessarily too much into the numerical values, though, in any case, even before we get to worrying about exponential holding times. We have a particular calibration that we did in that diagram that I showed you. But I do think that a dominant effect in determining the size of that bias is actually, there's a number of different parameters that enter into market calibration even before we get to worrying about the exponential holding times. So there's a number of different ways that I can imagine the changing the exponential holding times would potentially really cause a problem. I will say that if I think about it from a practical standpoint, if anything, I actually think the tails are potentially even lighter in many settings. So for example, if you think of bookings on Airbnb, it's a slightly different market where new listing nights become available every single day. And the lengths of bookings are not going to be kind of unboundedly large. So I think, and a similar idea would apply for other markets as well. So I think an interesting thing there to consider is actually a model where you have a different representation of inventory, where you have days of the inventory that can be booked into the future, and that might be a better way to capture some of the real effects that can happen in a real platform. But yeah, short story there. Have not done any sensitivity analysis with respect to changes there. I also think we can ask a similar question about the choice model and consider more general sort of non-parametric choice modeling there, and ask whether similar results would hold up. Our intuition is that these results hold up quite a bit more generally. So we've been working on developing sort of versions of these results that don't make the same types of parametric assumptions we've made in this paper. Yeah. My second bullet in a slide, when supply choice is low, competition can be low. Do you mean, let's see, my second bullet, when supply choice is low, competition can be low. Did you understand correctly? Let me see, I think you mean back here. Right here. So, right. So what's happening here is that when supply is low, the competition between listings becomes low. And that's just a mechanical effect that because we have less available supply in the marketplace, it also means that there's less opportunity for there to be competition between listings. So that's kind of what I meant there. I don't mean universally the competition is low, because in fact, in that regime, there's extreme competition between customers on that side of the market. Great, let me answer Nick's question, and then I'll wrap up the talk. So the TSR design works well on both extremes. In the middle, where supply and demand are roughly balanced, is there a way to choose parameters to produce a less biased estimate? Perhaps this relates to the improved TSR estimator you mentioned. Yeah, that's a great question, Nick, and that's exactly right. I didn't have a chance to say as much about that, the improved TSR estimator, but that's roughly the idea behind it, is that we develop terms that are trying to correct for that interference effect based on what we measure in this 4-cell experiment between treatment and control. I will say, however, just in the interest of full disclosure, that I really think we're in early days of fully understanding that optimization. So how do you optimally take advantage of the information that you get when you randomize on both sides of the market? I think that's still something where there's a lot of work to be done, and that's part of the work that we're on, that we have ongoing now. Okay. All right, so with that, let me actually just run into the last few slides here. I think I've got maybe like 3 minutes left, which should be just enough to wrap up the talk. So, first of all, just wrapping up this paper, I want to mention that there's a number of things that we're focused on. From an applied standpoint, we're interested in calibrating these experiments using market observables. That came up in my answer to Ton, that, I think something that is interesting about these kinds of models is that they're providing a lot of qualitative insight. And what's challenging is we still, in order to translate it to practical guidance, you have to be able to calibrate effectively. And so then the question becomes, well, what's the proper way to measure demand, supply, arrival rates, and to calibrate booking rates? So this is something that I think is a really interesting space of empirical work that we're doing. Related to Nick's question is, what are optimal TSR designs? And I focus primarily on bias in this talk. There's obviously variance as well. And so, there's probably an interest in minimizing mean squared estimation error. What would be an optimal design to trade off bias and variance, appropriately? Kind of another practical thing that's really interesting is not so much to focus on designing, optimal TSR designs on their own right, or optimal estimators. I should have said optimal designs and estimators, actually. But not just to design optimal experiments and estimators on their own right, but actually to use them to de-bias naive listing and customer side randomization. So that's really interesting because those naive experiments are run routinely in practice, and so using these designs to be able to de-bias them is a big emphasis. And then finally, how do we compute standard errors for these estimators? So that's related to the variance analysis and something that we're actively working on. I want to close by just briefly mentioning 2 alternative approaches that I think really, like, my goal in these 2 slides is, for this audience, one of my goals is to say there's a much broader universe of potential designs one could be thinking about here that don't look anything like what I described. So one is what's called cluster randomization. Good references here. There's a really nice paper by my colleague Johan Ugander called Graph Cluster Randomization, and a more recent application by David Holtz and co-authors at MIT and at Airbnb. So here the idea is pretty simple. It's basically that you group market participants into clusters and you randomize the clusters to treatment and control. So a very simple example would be, for example, if you're a ride-sharing marketplace, you might randomize cities to treatment and control and, observe full treatment in some cities, full control in other cities. What happens here is that your power is low, typically, because the sample size is small if you're only randomizing over cities. But the bias, your power is low, but the bias is also low, because now you're observing full treatment or full control in each city. And so there's an important question for a platform, which is to ask what functions, what market parameters should I be observing to help me determine whether that bias and variance trade-off is working in my favor with a cluster design. So that's one question. And then another approach that I spent some time working on, and this is what you saw in the earlier talk by Peter in this seminar series, is what's called a switchback design, where you alternate between global treatment and global control over time. So here the interference occurs temporally when the system changes from one policy to another, from treatment to control or vice versa. And Peter talked about this effect a little bit in his talk and described sort of an analytical approach that we took to studying optimal design in that setting by viewing the problem as one of estimating the difference in reward between 2 Markov chains. It's actually quite interesting to observe in online platforms, and this will be the last thing I'll say and I'll wrap up, that there seems to be a dichotomy where ride sharing and delivery marketplaces are active users of switchback designs. So Lyft, Uber, DoorDash, these are all companies that have written about the way they use switchback designs in practice. On the other hand, many other online platforms tend not to use switchback designs in their work. So online labor markets, e-commerce markets, it tends to be much less common. And one of the things that's intrigued all of us has been, well, what accounts for that? Is that optimal, or is it just sort of a cultural difference? And so we want to also do some analysis to try to understand settings in which one type of design is preferable to another. So I'll leave it at that. I'm happy to hang out for a few minutes and answer any additional questions. Thank you, everyone.
Thank you so much, Ramesh. So I guess since this is the end of the talk, maybe people can just unmute and ask. Maybe I can, maybe I'll take the privilege of being the host and ask some questions.
Sure.
Yeah. So you mentioned that there's a connection between the closed queuing network or queuing system with this model. I was wondering if instead of thinking of this as a closed queuing system, can I just think of the listings as servers? And then like when a customer occupies that server, it just becomes unavailable to other jobs. And then like if a customer cannot, like which is a job, cannot find a available server, it gets dropped from the system.
Yeah, I guess the reason I mentioned the closed queuing network analogy, Wena, was because of the state vector, which is the number of available listings in the system. So I guess you're right. Yeah, I don't think there'd be much difference in thinking of it that way either. I suppose the analysis pathway would look pretty similar.
Yeah. The way
yeah.
of picturing the system.
Yeah, that's right. I will say one of the reasons I used the language of a closed queuing network, actually, and this is probably revealing something about my own my own internal bias on it. I should have said more. The reason I said that is because I think there's an interesting alternate version of this type of model, which is something which is open. In other words, where the number of listings is not fixed over time, and where listings can arrive and depart as well.
Yeah.
And so I'm not really allowing that possibility in this model by fixing the number of listings to n. I think that a really interesting class of extensions around these types of models is something where you do allow that type of possibility. And then maybe layering one step on beyond that, something else that our model, I think two other types of things that our model is not really accounting for. One of them is that there can be endogenous response. So what I mean by that is that, if you imagine, I just talked about utilities in the abstract, but suppose the utilities actually capture response to prices, and prices are set by the listings themselves. Then it might be that the listings are adapting over time and changing the prices that they set in response to the demand that they see. There's a really nice paper by Kwang Zhu and Stefan Wager that looks at experimental design in a setting where there's long run price equilibration. And your goal is to come up with the designs and estimators that allow you to estimate that long run effect from a short run experiment. And I think like another thing that's missing in our model is the ability for things to change over the long run in a way that's not, so essentially what would be happening there is the parameters themselves would be changing over time as the listings adjust, say their pricing behavior, for example. So that's yet another dimension in which one could take things beyond what I talked about here. Yeah, but the open close things, like just to be fair, it was really because of that. It's that there's in the back of my mind, I've been wondering about a model where instead we have listings arriving over time. Yeah,
that's reasonable. Yeah, and another small thing is like now the customers are kind of like impatient, right? Like when they come, if there are no listings available at all, they will just drop, like due to the model. But there could be a potential where they are willing to wait for a small amount of time, and if something is available, then like the customer is going to stay in the system.
Yeah, I think that's right. So yeah, a couple other things I'll mention. I mean, especially given that there's been so much work on stochastic models of two-sided matching in the applied probability community. Yeah, I think a couple of things I'll mention. So one of them is, I talked about interference here, and there does appear to be a symmetry in the kinds of results I derive between the demand and the supply side. It actually turns out if you look, and we have a section on this in the paper, if you actually work out what's happening to the booking rates in each of these extremes when the market becomes supply constrained or demand constrained. In the demand constrained regime, it looks like customers are making a logit choice with the listings regenerating rapidly. It actually turns out that in the supply constrained regime, it looks like the listings are making choices over customers according to a logit choice model, and with the customers regenerating rapidly. And so if I think about what you just said, something where the customers could live for some time, what you're doing is you're gradually symmetrizing the model on each side.
I see.
So that now you have basically two-sided matching where each side, can kind of arrive, match over some period of time and leave. And I imagine that what you would start to see there is even more direct symmetrization in the behavior on each side of the market. I'll go back to what I was saying earlier, that our very strong conjecture based on the kind of analysis we've been doing since we finished this paper is that these results hold up in much greater generality than what I described in this model in particular. Because the underlying effects that we're talking about, I think, are fairly robust. We do, I think it's possible to think of examples that would break this kind of thing, especially as you start to change the structure of the choice model. But as long as the choice model is responsive to the available mass of each type of listing in the marketplace, I think you're going to see these type of effects. Yeah.
Yeah, thank you so much. I'm now going to dominate the Q&A session, so I'll let other people ask.
Sure, sounds good. I think there were a bunch of questions during the talk as well, so it might be not that many now. Should we wrap up there?
Yeah, sure. Okay, so yeah, so if there are no further questions, let's thank Ramesh again for the great talk.
Thanks, everybody, and thank you for having me again. Definitely great to be able to give a chance to. Great to have the chance to give a talk here. Thank you.
Thank you. So yeah, with that, I'll conclude today's seminar. Thank you, everyone, for being here.